the second session of the CILC.
Super, thanks a million. So welcome to the attendees, both in presence and online. And I would immediately like to leave the floor to Mattia Panettiere, that will present a contribution on very weak, essentially undecidable set theories. So Mattia, the stage is yours.
Okay, thank you, but my share tray is empty. I cannot share my screen right now. I don't know why.
I don't know. So possibly Parma can help in this.
Yes, we are going to check. You're supposed to, maybe you can try now, Mattia.
No, I cannot even open the share tray now. I'm sorry. No, it is empty again. Oh. I don't know what is happening, but the share tray is empty now. I don't know, maybe.
So.
Okay, I can try to. I don't know. I can try to close and reopen the application. I don't know.
Yeah, perhaps we can switch the first two contributions if Laura is ready to present.
Yes, I try to share my screen.
Yeah, great. So Laura from the Università del Piemonte Orientale will present a contribution on a framework for modular multi-concept lexicographic closure semantics. And please, Laura, the floor is yours. Meanwhile, we try to fix.
May I ask if you can see also the pointer on the screen? Or
yeah,
you can see it. Okay.
Yeah. Thank you.
Thank you. So this work was first presented in the workshop on non-monotonic reasoning last year, but it was not published. It's on the notes of the workshop. And so the paper deals with an approach for representing modular multi-concepts lexicographic closure. So the idea is to define an extension of lexicographic closure to the multipreferential semantics. But the problem is that I cannot move with the arrows up and down, and I don't know why. So I only.
No, it changes slide actually.
Yeah, but I have to use the touchpad, which is not well. I try to control the move. So the idea is to define this modular multi-concept extension of lexicographic closure in a description logic language where there are defeasible rules, conditionals, defeasible properties, and we modularize the knowledge base based on different modules. Each module deals with a different subject, a concept essentially. And this is an instance of the more general approach to the multi-preference representation that will also be used in the next paper to define a semantics for multi-layer perceptron in a different way. And so the idea is that in the semantics, from the semantic point of view, there are different preferences, each one associated to a module, a concept. And these preferences can be combined in a single global preference. The language in which we are working in this paper is description logic, the description logic CILC, where we have atomic concepts like mother of a doctor, female, and we have concept inclusions like a mother of a doctor. All the individuals which are mother of a doctor have a child who is a doctor. So the instances of concept C are also instances of concept D. And there are individual assertions of this form. For instance, Mary is a female, representing membership of an individual in a concept. And so the idea of the semantics of ALC basically is based on set theory. So two concepts, each concept is associated to a set of individuals in a domain delta. The individuals belonging to the concept, the females, for instance, and the intersection of concepts correspond to the intersections of their elements, and so on. An inclusion is satisfied when an inclusion C included in D is satisfied when all C elements are the elements. And preferential extension of description logic have been considered in the literature in the last 15 years, and they are represented in different ways, like typicality inclusions, like typical Cs are included in D, all typical Cs are Ds, normally C elements are Ds, normally birds fly, for instance, and this kind of inclusion are regarded to be defeasible, that is, they are not strict. They may have exceptions, and they are used to ontologies with exceptions. And this is a way to import in description logic the notion of conditional assertions from Krauss, Lehmann, and Magidor preferential theories. And in a preferential description logic, the semantics is defined through a triple, a set of a domain, a set of individuals, an interpretation function which assigns to each concept the set of individuals consisting in belonging to the concept, and this is the delta and the interpretation function. They are like in standard ALC. And the preference relation describes the preference among individuals. So X is preferred to Y when X is more normal than Y, is more typical than Y. And usually in KLM logic, as well as in this extension we are looking at now, there is a single preference relation. And in this work, we are moving to a situation, to a semantics where there are multiple preference relations. A preference relation can be used to define the typical C elements, which are those C elements which are minimal with respect to the preference relation. And depending on the property of the preference relation, one might have different kind of interpretation. In particular, when this preference relation is a partial order, is a well-founded partial order, and when it is also modular, we have a ranked interpretation. And we will mainly consider ranked interpretation and combination of this kind of ranked interpretation. And so these semantics have been based on minimal canonical rank models have been considered for this kind of preferential description logics. And there is a well-known construction called rational closure, which is a construction rather than a semantics, but it has a semantics, of course. And the idea is that rational closure, starting from a knowledge base, so a knowledge base in this kind of logic is represented by a set of strict inclusion and a set of typicality inclusions. For instance, PhD are students, PhD students are adults, employees are adults, primary school students are children, and so on. These are strict inclusion. Then we have defeasible inclusion, like normally students do not have a scholarship. Normally typically students are young. Typically employees are not young. Typically PhD students have a scholarship, and so on. typically PhD students are bright. So the rational closure, starting from a knowledge base containing strict and defeasible inclusion, gives a rank to the concepts and to the defeasible inclusion, where well, the less atypical concepts have lower rank. So while exceptional concepts or more specific concepts have a higher rank. For instance, here the rank of students is 0, the concept student is 0, while the rank of concept PhD student is 1, as PhD students are students, but yeah, they are exceptional as they have scholarship, while normally have a scholarship, while normally students do not have a scholarship. So the higher is the rank, the more specific are the defeasible properties and the concepts. This is a criteria used often in non-monotonic description logic. One wants to give a higher priority to specific properties. If I have a PhD student and I want to know if a PhD student has some property, has a scholarship or not, well, I will use the specific property for PhD student rather than that for student, which is less specific. The problem of rational closure is that on the one hand, it is too weak, as for instance, PhD students do not inherit the property of student, which is of being normally young. So the fact that PhD students are exceptional with respect to students for they have a scholarship, makes all other defeasible property of students to be lost. And this is a problem of a blocking inheritance problem is called. So in this respect, rational closure is too weak. On other respects, it's too strong. And as we will see in some example later. And so the kind of solution we are exploring in this work and has been explored in other work in the literature is that of considering more than one preferential relation. And for instance, like the preference relation associated to student and preference relation associated to employee, as an individual, Bob may be more typical than Tom with respect to being a student, while Tom may be more typical than Bob as an employee. So this is the idea of having multiple preferences, and there is several work, both on extension on the rational closure to avoid the inheritance blocking, and on the use of multi-preference semantics. So the intended semantics we want to get, more or less can be represented like this, where we want to consider a modular structure of the knowledge base, where each module is associated, a preference relation is associated to a concept, for instance, student, and associated to a preference relation, which ranks the words, the element domains with respect to their typicality as a student. On the other hand, concerning employee, we have a preference relation ranking the individual elements, the elements of the domain with respect to these concepts. And of course, we may have an element, as we have seen, Bob may be preferred as a student and Tom may be preferred as an employee. And in this case, we globally, we define, we cannot define a preference among these two elements. In a modular multi-concept knowledge basis, we have different modules, and each module is associated to a subject. For instance, we have two modules, where module M1 is associated to the subject student, and it contains all the typicality properties for students and subclasses, essentially, PhD student, employee student, and so on. And module 2 contains all the properties concerning employees. So it's not the case that M1 and M2 are disjoint. We do not have a partition. We do not require to have a partition of the knowledge base. And there are other options, and in particular, one option will be considered in the next paper I'm going to present. The other option is to have smaller module, in which each module contains only typicality properties concerning a single concept. For instance, student, and not for instance, I have a module for students and I have a different module for PhD students, and I do not put together typicality properties, typicality rules concerning different concepts, even if concept and subconcepts. So the idea of this paper, I will not define in detail the kind of semantic construction, is to generalize the notion of lexicographic closure, which is a refinement to multiple modules. The lexicographic closure was defined by Lehmann in 1995 in the case of classical logic, and extended, the construction was extended by Casini and Straccia to the description logic CILC. And the semantic of Lehmann's semantic based on which is a preferential semantics, can be extended to description logic. The kind of semantics is very simple. The idea in case of Lehmann's semantics is that of comparing by a preference relation two words, giving higher preference to less exceptional words, which are those violate less serious defaults, where seriousness is defined here in lexicographic closure based on the ranking given by the rational closure. So I prefer those words which violate less specific defaults, and less default also. I also prefer the words violating less defaults. This can be extended to the description logic case, if we consider for each module a preference relation, we can define for each single module a ranked model, essentially, like for employees and for students before. And in this way, I can use the preference relation associated to the module student to evaluate the properties of typical students. How can I evaluate the properties when I'm dealing with more complex concepts, like are typical employed student high? So the problem in this case is that I do not have a single preference relation. I have two. I have the preference relation with respect to students and the preference relation with respect to employees. And so I need to combine them. And a simple way of combining preferences is to use the Pareto combination. And a slightly more sophisticated way also deals with specificity. So the idea is to define this global preference by a modified Pareto combination, and the resulting structure we get is a preference relation and has the property of preference relation, so satisfies the KLM properties and so on, and so as some wanted properties. And by this construction we define this combined lexicographic modules, and also define an entailment relation, which has good properties from the point of view, from the logical point of view, satisfy KLM properties, avoids the drowning problem, so the blocking problem of rational closure, and also avoids an unwanted conclusion of rational closure, as one can see that now I cannot show you the example, but one can see by an example which was already a variant of one already given by Geffner and Perl, the problem that rational closure does not deal properly with ambiguity preservation. That we have an ambiguous knowledge base from which we cannot conclude that, for instance, that PhD students are homeowner or are not, because Italian PhD student, because Italian normally are homeowner, PhD students normally are not homeowner. What about typical Italian PhD students? So I cannot conclude anything. But in this case, if I add some information which seems not to be correlated, like the typical student do not have scholarship, while PhD students have, well, this is enough to conclude that typical Italian student is not homeowner, and this is unwanted. So separating, the idea is that separating the, if I can find the solution that is can be adopted in this setting is that of separating essentially the information relating to Italians and the information relating to PhD students in different modules, and in this way one avoids this problem with ambiguity preservation. There are other solutions in the literature, but which are very sophisticated, and this seems a simple solution. And general combining preference is a simple approach, which may give a framework in the sense that depending on the granularity of the aspects, they may be concepts or they may be modules, as in this case. And the kind of preference relation one defines, here we have used lexicographic closure, but we could use another semantics, as we will see the next talk. And the notion of specificity can be used to deal with the fact that some concepts are more specific than others. And in general, we might want to have hierarchies of modules. And so, depending on all these aspects, one can have different kind of different kind of semantics. And so that in the next talk, I will deal with another instance of this semantics, which has been first introduced to deal with plausibility, to deal with the semantics of self-organizing maps, which shows that the notion of semantics based on multiple preference may be plausible. And well, in the next talk, we will adopt this to provide a semantic for multi-layer perceptrons, which are deep neural networks. And there is much work on multiple preferences. And I want just to mention a work on an algebraic framework for preference combination, which has been proposed by Bozzato, Eiter, and Kiesel, and published on TPLP recently, and will be presented in the CILC. So here we have used Pareto combination of different preferences, but more sophisticated way of combining preference can be used, and this paper deals with this kind of approach. Thank you. I've concluded.
Thank you, Laura, for the very interesting talk. Before going on with the next one, I would like to ask the audience if there's any question or doubt that they want to be answered.
Yes, maybe I have a question now.
Please. Who's speaking? Giuseppe Bisicchia? Yeah, please.
I don't know if it makes sense, but it makes sense, or how it's possible to make inferences for a module combining, maybe doing the intersection of other modules.
Considering intersection operators on modules, you mean like intersection, union, and things like that? Yeah, it might have sense. And actually, the kind of combinations considered by by Bozzato, Eiter, and Kiesel considers this kind of more sophisticated approach, where you have modules, you have preferences within modules associated with the modules, and then you can combine by using algebraic tools to define the kind of combinations. This is maybe reasonable. And well, in the case modules are just associated to concepts and they contain just typicality relation for a single concept. Actually, concepts are built from using union, intersections, and so on. So the issue of defining the typicality of a concept, which is an intersection, for instance, the intersection of two concepts, student and employee, whether this can be defined compositionally from the preference relation for employees and students, this is an issue, of course.
Okay, thank you so much.
Thank you.
Thank you. Is there any question, perhaps also from Parma, which I don't see, but it would be nice to interact with people back to normality?
No questions from Parma.
So perhaps we can move to the next talk still by Laura, so which is also linked, as she mentioned. So perhaps new questions will arise with this. Okay, now we see Parma.
I try to be short because maybe I have been too long in the previous.
No, perfectly on time. We started a little bit later, so.
Okay.
Please.
Thank you. So this in this talk, this talk was given in Gelia in May, and this talk deals with weighted defeasible knowledge bases, and they are used for their relation with deep neural networks. So the idea is that of defining the aim of the talk is to investigate the relationships and weighted knowledge bases essentially are knowledge bases like those we have seen in previous talk, however, here there are weights associated to the typicality inclusion. And here we consider also a fuzzy extension of these fuzzy semantics for these weighted knowledge bases. And so what we will see is that on the one hand, we can characterize, so a multi-layer perceptron is a simple deep neural network, and we will see how it behaves later. And so the idea is that we want to model the input-output behavior of the network, and we can do this by building a model, which is a preferential model, which is a multi-preferential model, where essentially we associate a preference to concepts. In this case, we specifically associate concepts to units in the network. Imagine an output unit of a network where which represent the fact that you want to see if the image you give to in input to the network are representing horses or not. And so you have a unit whose activation gives you the information. And so the idea is that by associating concept to units and preference relation to such units, we can define a multi-preference model describing the input-output behavior of the network. On the other hand, one can also see that a multi-layer network can be regarded under some condition as a conditional knowledge base, a weighted conditional knowledge base. One can establish a correspondence. Why this can be of interest. It can be of interest from the standpoint of explainable AI, to understand which is the logic underlying a neural network, and it can be of interest for the verification of properties, as when you have a neural network and you can characterize the behavior, the input-output behavior, for instance, of the network by a model. It might be a preferential model, it might be a fuzzy model, as we will see, or a mix of the two. You can then use model checking in the proper logic for verification of properties. Looking at the network as a deep, as a knowledge base, on the other hand, allows for a combination of empirical knowledge with symbolic knowledge, essentially. And for instance, one could use the network for computing the weights of conditional and combine the network with other conditionals and verify the consistency of a neural network, for instance, or doing things like that. Of course, here we are working at the very low level, because as we will see, that we will associate conditional implication to the synaptic connection in the network. So from the point of view of the logic, the motivation are the same as before, and I will not enter. And again, I will not enter in the definition of the logic. Here we are considering a smaller fragment than an ALC. Of course, the logic can be defined for ALC or for any description logic, the typicality extension we have. But for the kind of, for modeling the neural net, capturing the logic of neural network, it's enough a very simple logic. And we only use concepts and not role. So we can even restrict to a logic with no roles. And from the knowledge base, from the knowledge representation point of view, our knowledge base will look as follow. So we have a typicality inclusions like before, but with a weight. The weight is a real value, and represents the plausibility of the typicality inclusion of the property. For instance, we might write, we might have a set of typicality inclusion describing the property of a horse, saying that normally horse have long mane, normally horse run fast, and both of these have weight 20, and we may have also negative weight. For instance, normally horses has stripes as weight -80, because we do not believe that that an individual having stripes might be a horse. And so if we have two individuals, spirit and body, where spirit has long mane, has tail, no stripes, and does not run fast, we might associate to spirit a weight with respect to this property of being a horse, summing the weight of the defeasible inclusion that which are satisfied. So spirit has long mane 20, has tail 50, no stripes, so we don't subtract 80, and does not run fast, so we don't add 20. We have 70. And body instead has long mane, has tail, run fast, and has stripes. So 20 plus 20 plus, all of these are satisfied. 20 plus 20 plus 50 minus 80, it's 10. So spirit is preferred to body. If we just look at the count of the weight of the weight of the satisfied defaults. So this is very simple, a simple way of evaluating, of comparing the typicality of two individuals. And this is actually in a slightly different way. It's used in C representation, introduced by Kernis-Berner and Bayerle, and studied by her and their colleagues. in the last 20 years. So the logic I'm introducing is not that new. It's very similar to other kind of non-monotonic logic, not that ad hoc, let's say. So this construction allows us to associate which individual, given a concept like horse, a weight, summing the weights of the satisfied inclusion. Otherwise, if the individual is an instance of the concept, it is an horse. Otherwise, the weight is minus infinity. How can we use these weights? We can use them to define the preference relation with respect to concepts. So for the concept horse, as we have done before in the example, we can define a preference relation. Here it is not a strict preference relation. Here we have a preorder, but one can be defined in terms of the other. And so X is at least as preferred as Y with respect to concept Ci if the weight of X with respect to that concept is greater or equal than the weight of X with respect to Y. This kind of construction allows to define preference relation for horses. So all the elements of the domain are given a value which allows to rank these elements. And this representation corresponds to a ranked model defined by this preference relation. The typical horses are inside, the less typical are toward the outside. Outside, we have the individual which are no horses, which are not horses. And we may have for some concepts, we may have a situation in which the individual of the two concepts belonging to the concept with different degrees overlap. And so how can this be used to define, so essentially this notion of multi-preference interpretation, which is defined as we have seen in previous paper essentially, how can be used for neural networks? A neural network can be represented as a graph. It's a feed-forward network when the graph is acyclic. These represent the input layer, the input units, and these are the output units. We may have several levels of hidden units, and there might be feedback. So the graph might not be acyclic, may have cycle. In this case, the network is recurrent. And in general, I will go a little bit. In general, each unit is connected to a set of input unit, which each one gives an input signal to the unit K, and there is a weight associated to the synaptic connection between each unit J and unit K. And the network, given some initial, the signal, given the signal for the input units, it computes the signals for the activation of the next of all the units in the network, and it is done by computing by a system of equations which define how the activation of the neurons can be computed. And essentially, there is this sum. So the value of the activation of all the neuron, the input signals are multiplied by the weight and are summed, and the result plus a bias is applied an activation function which is used to map the resulting value to an interval, usually 0, 1. So at the end, each neuron K will get a value in the interval 0, 1. And so how can we build a model of a multi-preference model for a multi-layer perceptron? For each element, for each input stimulus, we build a model on the domain of input stimuli. Suppose we consider the domain of input stimuli used for training or also for generalization. Anyhow, given a domain of input stimuli, we look at the activation of the different neurons in the network. And for instance, this neuron K, for each input x1, x2, x3, will be activated with different activation value, and these values can be used to rank the individuals and to give a preference to the different individuals. So X3 is an instance of concept CK associated of neuron K with membership degree 0.8. See, if this neuron K represents the concept horse, and normally we don't know the meaning of hidden units, but we know it for the output units. So the fact that the activation is 0.8, it means that X is very plausibly an instance of the concept K, a horse, while X2 is its membership in the concept is only 0.3. So these values can be used both for defining a preference relation associated to this neuron, but also to define a fuzzy interpretation, where each concept associated to each neuron is interpreted based on these activation values for the different inputs. In a fuzzy interpretation, a concept is interpreted as a function which assigns to each element in the domain a value in the interval 0, 1. So we have not just true or false, but we have a range of values, and the value of the value given by the value of an assertion C of X is a value in the interval 0, 1 and represents the degree of membership of X in the concept C. So based on this notion of fuzzy description logic have been studied in the last 20 years, and they have been very well studied, and this kind of fuzzy description logic can be used, and their semantic can be used to define an interpretation associated with the network. Of course, we don't need to have a concept associated to each unit, but we may just associate a concept to the interesting unit for us, just for instance to the input units and to the output units, so that we can describe the relationship within the input and the output units. Given this kind of interpretation, we can evaluate whether concept I is concept C is included in concept D to some degree, because in the description logics, where is it? We may have axiom like this: C is included in D with degree higher or equal to 0.6. Mary's blonde with the degree greater or equal to 0.8, and so on. So given this kind of model, we can evaluate fuzzy axioms. Putting together, of course, here we have a fuzzy model, but as we have seen, this fuzzy value, the value of this fuzzy concept induce a preference. So we can see this as a combination, also as a combination of a fuzzy and preferential model, a fuzzy multi-preference model. And we can define the notion of typicality with respect to some concept using the preference relation with respect to the concept. Based on this, one can, and I conclude, one can see each processing unit, can associate to each processing unit a set of conditional conditional inclusion, one for each synaptic connection entering in the unit, where the weight is the weight associated to the connection. And this set of defeasible inclusion, putting together all the defeasible inclusion for all the concepts, we get a defeasible knowledge base. And one can see that the multi-preference model one can construct from the input stimuli over the set of input stimuli is indeed a model of this knowledge base in the logical sense, using a weight, but well, using semantics for weight and knowledge bases extended to the fuzzy case. So we have seen before just the case of the two values. And so to conclude, I just want to mention that there is much work on this, on the relationship between neural network and symbolic reasoning, which has given rise to new models, has given and to different approaches to combine symbolic reasoning with neural networks. There are many, well, there are some old results on the relationship between ASP and neural networks and the TP in neural networks. And well, there are many open problems, some decidability results. There is well, the problem of if the notion of entailment coming up from in the fuzzy case is undecidable, the problem of dealing with multiple values approximation, and ASP and constraint solver can be used to develop proof methods for this kind of logics. There are also several issues concerning revision, relation between learning and revision, temporal extensions of this kind of formalism. As well, as far as what we have studied only deals with the stationary behavior of the network, and the network we assume it has been trained, and we describe what it represents. So the meaning of the trained network. Thank you.
Super, thank you. Thank you again for the very interesting talk. And now we are ready to collect maybe one question from the audience. Even in Parma. Otherwise, I have one. Oh, okay, there is one from the audience. From Giovanni. Please. Turn on the mic.
Yeah. Thank you very much for the presentation. I mean, that was a kind of a direction that I also was interested to develop, although utilizing other methods. But I have one question, because you're like opening up the black box by looking what are the preferences that you can construct according to the neurons and the connection that you have, the weights that are across the neurons. But then in practice, how much this is sensible to us? So how much that makes sense for us to intervene at this low level, in the sense that typically what makes sense, it's outside of the network, no? So because there may be weights that are assigned to certain value just randomly, because in the training process, that was the best allocation, but that has no meaning at all. So we are interpreting that as meaning, but there is no meaning there. So I wonder whether you have like interrogated about this issue, whether you were exploring some other ideas. So,
well, concerning so let us consider the idea of building a model from the network, the trained network, looking at the behavior of the network on the set of training example. In this case, one, of course, may focus the attention on some units, and using the typicality operator, which of course one can consider other kind of notion of typicality. So in this case, taking the typical elements, maybe you can take a very small set of elements with respect to all the elements, but if you consider a set of typical or most typical elements, you may recognize which you can recognize some properties which which maybe allow you to avoid considering outliers. For if you consider all the elements with which you have trained the network, but for a single unit, maybe there are many outliers, but it's not so likely that they will be typical instances of that unit, that concepts. So if you focus on the typical instances, you may expect to have some regularity,
some meaningful regularity. So you're capturing something which makes sense according to what was trained. Yeah, no, then that makes sense. Yes. So in a practice, the typicality is a kind of filtering or denoising or whatever it is happening into the.
Yeah.
I'm really curious what's happening when you apply that on a real neural network. So how much, if you want, of noise component there is, and how much of conceptual components is there? Yeah,
in fact, what we have not yet done is to look at real cases and to try. So we are starting to do that. We have not empirical results, an empirical valuation so far. So this result is just theoretical. So this is what is missing.
I'm sorry to interrupt the discussion, which is very interesting, but time is bad. So we thank you, Laura. We move forward to our first speaker, actually. So we go back in time to Mattia Panettiere, which now should be able to share the screen.
Okay, I am.
Super.
Okay. Can you see the screen and the pointer?
We see the pointer, but not the screen yet.
So, okay, maybe it is better if I do it like this. Okay, can you see the screen and the pointer now?
No, I mean, at least I see a black screen.
Okay.
I don't know whether
I expect another problem.
It is possible to broadcast the slides from Parma, maybe.
I guess it is. I've sent the slides to
that would be...
Yes, we can broadcast and just give us a couple of minutes.
Yeah, now we see them.
No, now we see it. Now we see
it. Can you still see them if I go in presentation mode?
So, yes. Mattia, the floor is yours.
Okay, thank you. Hello to everyone. Today I will show you some very weak set theories which are essentially undecidable to another very weak class of formulas. So we will start with some preliminaries. We said our formula is delta zero if every one of its quantifiers are bounded. That is, they are either of the form for all x in y or exist x in y, which are defined in the usual way that you can see in the slide. We said that a delta zero formula is of complexity on if it is equivalent to a normal form formula with n minus one quantifier alternation, starting with a sequence of universal quantifiers, which can be possibly empty. So the important things here are two. We consider the number of quantifier alternations in the formulas, and we want to have bounded quantifiers. We say that a theory is undecidable with respect to a class of formulas if there is no algorithm that, given a formula in the class, outputs whether there are sets that make the formula true. And we say that the theory is essentially undecidable if every one of its consistent and recursively axiomatizable extensions is undecidable with respect to some class of formulas. So in general, as you can imagine, proving essential undecidability is not an easy task. But it is very similar to the property of the second Gödel incompleteness theorem, which speaks of essential incompleteness, that is, incompleteness for every consistent recursively axiomatizable extension when we can express arithmetic. While incompleteness and undecidability are usually not related, in this specific case, as we consider classes of existential closures of delta zero formulas, and since A positive answer to the decision problem for a formula implies that the existential closure of the formula is true, and a negative answer implies that the negation of the existential closure is true. We have that as we are considering consistent theories, indeed, we have that desirability implies completeness with respect to one of these classes of existential closures of formulas. So the plan is to prove essential incompleteness for the theory, so that taking the contrapositive of the implication that you can see here, we have essential undesirability. The language that we consider is one of the simplest set theoretical languages. We consider a first order language with equality and just a single predicate symbol, which is the membership symbol, and we have no function symbols. So the only terms that we have are single variables. We consider extensions of a core theory, which is very simple, and that's the 4 axioms that you can see. One stating that there is an empty set. The second one stating that taking 2 sets, we have the set that is composed by the elements of the first plus the second set. And the third axiom saying that if we have 2 sets, we can remove one from the elements of the other. And the regularity axiom stating that every set has a minimal membership, minimal element. We consider indeed extensions of this core theory that have some specific properties, and in particular, it will be useful to consider these 2 examples. One in which we extend the core theory with an instance of the separation axiom that says that we can filter the elements of a set satisfying some formula, and one in which we extend the core theory with a finitude axiom stating that the universe is the one of finite sets. So we already knew from the literature that in the core theory, we have essential undesirability with respect to for all exists for all 0 formulas, which are delta 0 formulas of complexity 3. So we have 2 quantifier alternations at most. And we have shown that taking these light extensions of the core theory, we can have essential undesirability with respect to for all exist 0 formulas. So just one single alternation. So our objective is to prove an argument similar to the second Gödel incompleteness theorem. So in order to do so, we have to express natural numbers and recursion theory, and we have to do that with for all exist 0 formulas. Then we have to find an encoding for formulas and an order for in this encoding, and we have to be able to express all of these with for all exist 0 formulas. After that, we have an encoding for formulas. We have to define a for all exist 0 predicate that this proof xy predicate that holds whenever y is an encoding of a proof of some formula which is encoded by x. And we have, again, to do that with for all exist 0 formulas. And once we have done all of this, we can proceed proving a diagonalization lemma and proceed with an argument which is very similar to the usual Gödel argument. Now, as you can see, we have to craft a lot of for all exist 0 formulas, and the for all exist 0 language is a very weak language. So expressing even the simplest of the concepts that we are used to in mathematics might become complex. We realized that using functions, pairs, and tuples is essential in crafting low complexity delta 0 formulas. And what we did is something that reminds me loosely of what programmers do when trying to optimize some program. They pre-compute some values and store the pre-computed values in some suitable data structure. And then if the data is easily accessible in the data structure, they might see an improvement in the time complexity. Here we have no time complexity nor space complexity or something, but in some sense we can use the functions as if they were data structures where we store informations as if it was metaphorically pre-computed. You will see more concretely what I'm talking about. But first of all, we have to make sure that functions are expressible. The functions are cheap in general, so all the concepts related to functions are expressed by low complexity formulas. The classical notion of pair that works under regularity is the classical definition is the one that you can see in this slide. And as functions are made of pairs in set theory classically, we can imagine this is the most basic thing that we have to study. This is problematic indeed, because just to express the extraction of the second projection of this pair, we have to use an exist for all zero formula. As you can see here, we have an exist quantifiers and then nested a for all quantifier. And this is problematic because it is already a for all exist for all zero formula, which has complexity 3, while we want to do the whole work with complexity 2. So we wouldn't even be able to start with this definition of pair. So we opted for a more complex definition of pair, which works under our axiomatic system, which is the one that you can see in this slide, and where we can express a component extraction with exist zero formulas. Then using this definition of pair, we can also define all of the other function-related concepts with cheap formulas. For instance, function application is expressed by an exist zero formula, or the domains of functions are expressed by for all exist zero formulas. Then the first point in our list was to express natural numbers with for all exist zero formulas. Now, this is pretty problematic because we have in some way to express finitude, which is really hard to express in a weak theory like this one. So we noticed that if we add a single instance of the axiom specification to the core theory, this formula characterizes finite ordinals, which are the usual representation of natural numbers. And the positive thing of this definition, even though it is for all exists for all zero, because this z plus equals y here hides a universal quantifier, so we have a universal and existential, and then again a universal hidden here. So even though it is for all exists for all zero, this definition here shows clearly what is the problem. And the problem is that we have to express the successor of an ordinal with a universal quantifier. So we decided to abandon the idea of characterizing finite ordinals with for all exist zero formulas, and we decided to go for a more complex structure that behaves like natural numbers. So we have all the interesting properties that we need of natural numbers, and that allows us to express successors with exist zero formulas, so that this becomes a for all exist zero formula. And indeed, our definition of natural number is that we see natural numbers as quadruples, where the second projection is a finite ordinal, which is the classical representation of the number that the whole quadruple represents. The first projection is its predecessor, the third projection is its successor, and the fourth projection is a function mapping all the finite ordinals which are below the number represented by the quadruple to triples containing their predecessors and their successors. So what we have here is that the first 4 lines in this definition enforce this quadruple structure that I've described. And the last 2 lines are essentially the same lines that we have seen in the definition and in the characterization of finite ordinals. The only difference here is that indeed, instead of z plus equals y, which was the problematic thing in this formula, here we can access the successor of z, which is a number which is below x, just using existential quantifiers, because we can use the map which is in the 4th projection. So we extract the 4th projection, then apply the number which is below x, and then we take the 3rd projection, which is the successor of z. So this one is a shorthand for successor of z, and we do all of that using just tuple projections and function applications, which are exist zero formulas in our setting. So this is a for all exist zero formula. Regarding codes, we decided to use a very straightforward definition. We consider codes of formulas, I mean. We consider the syntactic tree of a formula, and we say that a code is a sequence of nodes of a binary syntactic tree, there is. And we see the nodes of the tree as triples containing as first symbol the label of the node, and as first projection the label of the node, and as second and third projection is its left and right children. In the case in which the node expects a variable as a child or a term which is a variable in our setting, the number in the child is an index of the variable in a standard ordering of the variables. If we expect a subformula, so for instance, for the equality symbol, we have the equality expects term as children. So the two numbers here are indices of variables, because terms might also can only be variables. So for instance, equals 3, 4 is v3, ni3 equals ni4, and in 4, 5 is ni4 in ni5. When we have nodes that have subformulas, in the place where we expect a subformula, we interpret the number as an index in the list to the node, which is the root of the subformula. For instance, this quantifier here expects as a subformula this ni4 in ni5, which is the subformula rooted in the node 2. So this node here represents this subformula here, and so on and so forth. So by convention, we say that the last element of the node is the root of the tree, and the only exception in the function, the code function, is the first element, which is a natural number, which is an upper bound for all the values in the triples. And the reason is that in this way, fixed the first value, which we call height of the code, fixed on height, we have a finite number of codes, so we can easily define a total order for codes. And indeed, we define a total order for these codes, which has to be for all exists 0. And we do that in a straightforward way. We first, taking two codes, we first compare the height. If it is the same, we compare the domains. If they are the same, we compare the triples. And we compare the triples viewing them as natural numbers in base h, where h is the height of the code, since the height of the code is an upper bound for the values that we find in the triples. So the triples can be seen as triples of digits in base h, where h is the height. So we can do all of that with for all exists 0 formulas, and we can also define next a successor predicate for codes, so that we can work in this total order. We have defined codes for formulas, and now we have to define this proof predicate. In order to do that, we have to be able to find out if a formula is an axiom, and we have to find out if a formula is obtained in a fair way using inference rules. And to do that, we have to solve many smaller problems. And we use the usual technique of using functions as data structures. So for instance, to check if a variable is bound, we have defined this bound list predicate. So for each code, we build these functions that map the nodes of the code to sets containing the indices of the variables, which, if occurring in that subformula, are bound variables. We have to check if two codes are equivalent, and we have to do that often. For instance, when we have to check if the modus ponens is applicable, and we cannot use the equality symbol because we might have we actually have infinite codes for each formula, so the equality symbol might fail. And we have defined these predicates which use similar techniques, which essentially state that our code is in normal form, which can be compared using equality. And we use another time similar techniques to understand that a code is a formula which is obtained from another formula by renaming. So with all of these techniques, we finally defined what proofs are. And to us, proofs are tuples, where we have a list of all the subformulas of the formulas that occur in the proof, so that we can always compare this proof. And we store them in triples, where we have the left subformula and the right subformula of each formula, so that we can compare all the parts with equality always. And then we have a list of indices pointing to the subformulas in the first list, which is the actual proof sequence, as classically seen, of axioms and things obtained through the application of inference rules. And then we have a list of bound lists for each subformula, so that we can check if exists 0 formulas through a function application if a a variable is bound or free, and then a list of the domains of the codes of all the subformulas. And we have that because domains take for all exist 0 formulas. And if we store them in a function, in this list, we can access the domain of the codes with exist 0 formulas. So it is, again, the same technique. So with this definition, by some other technical consideration, we can apply the usual Gödel arguments, and we reach the main result of the work, which is indeed that given any extension of the core theory where natural numbers are expressed by for all exist 0 formulas, we have essential undecidability with respect to the class of for all exist 0 formulas. And for instance, we have the two examples, which are the extensions in which we have one single instance of the axiom of separation, because we can use that definition of natural numbers, and the example in which we have an axiom for finitude, because in that case, natural numbers become ordinals if the universe is finite, and ordinals, when we have regularity, are expressed by for all 0 formulas. So we think we can tighten the class, tighten the axiomatic core under which everything works. And what I mean is that we can return back to the original axiomatic core, for which it has been proven that we have essential undecidability with respect to for all exist for all 0 formulas. So without extending the core, I think we can apply the same argument, but using similar techniques and exploring alternative definitions of natural numbers. And another thing could be to tighten the class of formulas, maybe in other sides, not just the delta 0 complexity. Thank you for your attention. Do you have any questions?
So thank you, Mattia. We have maybe room for a very quick question. I don't know whether the audience or here is Agostino. Please.
Yes, thanks. Now I have a question about the encoding in the slides number 11. I don't understand how you can check when the number is a subformula or a variable. It would be possible to use different numbers, for instance, and have a bound for variables and use other numbers for subformula, for instance. I don't understand why there is this ambiguity.
Okay, yes, I understand, and we have thought of that, but the thing is that given a symbol, it is already clear what its left child or right child should be. For instance, for the equality symbol, we know that the left and right children are both terms, so they have to be variables. For the universal quantifier, we know that the first child is the bound variable, so it has to be a variable index, and the second variable has to be the subformula inside the scope of the quantifier. So the third projection of a universal quantifier node is always a subformula. The second projection is always an index of a variable. When we have implication, for instance, with implication we have that both the children are subformulas, because the atoms are the literals are either with equality or with the membership symbol. So when we have the right arrow, the implication, we are sure that the two children have to be subformulas.
Okay, thanks. I've understood it.
Great, thank you, Mattia, again. Thanks, Agostino, for the question. Now we move to our last speaker, which is Matteo Pascucci. Hi, Matteo.
Hi, thanks.
Yeah, great. So the floor is yours. And Matteo will talk about geometry of Hohfeldian relations.
Thanks. Okay.
Can you share the screen?
Trying to share, but it is temporarily blocked. Let's see if it works. doesn't work probably.
Otherwise, we have Giovanni here. That
Yes.
I can try to share mine.
Yeah.
Yeah.
Let's see whether you see something.
Yeah, great. We see it.
Okay, so I will. I need to close this thing. It's not full mode. What do you see? That's a
good browser, but I think it's fine.
I guess it's really the browser, this one. Let me check a moment. I did the PDF. It's better.
Yeah. Super.
Yes. Okay, Matteo, I will...
yeah, you have to go, sorry.
So Giovanni will be the human driver of the mouse.
No, please deliver the talk because my computer is currently blocked, so I have to restart the program again.
Oh, do you want I start?
Yes, please start.
Okay. So, well, so welcome everybody. So my name is Giovanni Sileno, and I will talk of a joint work that we did together with Matteo Pascucci about the geometry of Hohfeldian relations. So this work aims to enrich the analysis of Hohfeld's framework on normative concept, which was presented for the first time 130 years ago. And we individuate and formalize three distinct families of power. And we do that by referring to Aristotelian square or square of oppositions. And then we kind of clarify better the logical relevance of Hohfeld's analysis. And also we expand the squares into hexagons to solve certain symmetry issues that were observed into the literature. And then we highlight, if there is time, some connection between the various notions of powers and potestative and deontic concept. So first of all, let's start from who is Hohfeld. So he was a legal scholar 120 years ago that presented this taxonomy of concepts that are used as they used in legal judicial reasoning. And there are two levels of concepts. So the first order concept, it's about the deontic concept, so duty, claim, no claim, and liberty. And the second order or potestative concept, it's about power, liability, immunity, and disability. So the second order, they are called like that because it's about modifying positions in the first order. And all these concepts can be read as ternary relations amongst two normative parties. So this was another point of the framework of Hohfeld. There is no normative position which is standing alone. So if there is a duty somewhere, there is always a person who is claimant of that duty. And that's about a certain behavior. So here will be about a type of action. So the Hohfeldian framework is presenting by using two squares. So these are the two squares. So as you see, there are always two parties involved for any type of position. So if I have a duty, so that means that there is another party that has a claim. If I am at liberty about doing a certain action, so there is another party that is in position not able to do any claim, of no claim towards me. While on the other hand, if I have the power to command someone to do something, that means that someone is subject to my power, so is liable. On the other hand, if I'm disabled, I don't have this power, so the other part is immune with respect to my power. On the other hand, we looked at another type of diagrams, which is very well known, which are Aristotelian square or squares of oppositions, which is a kind of really classic structure to visualize concepts. And this structure is used like very often in literature studies or semiotics today in contemporary times. So the Aristotelian squares have been designed for a lot of modalities. This will be the deontic modality. So we see what kind of relationship are on the square, and the colors are meant here to help with that. So if someone is obligated to do something, so that means that he is permitted to do so. So this is a subaltern relation. While if someone the obligation is contrary of forbiddance, on the other hand, one can be permitted to do or not to do something. So these two, the E and O positions, they are called subcontrary. And the important point is also that forbidden and prohibition, they are really contradictory points. So the negation of prohibition, it's a permission to do, according to standard deontic logic. So we can rewrite the ternary relations amongst the two normative parties and an action type utilizing just one of the primitives. So in this case, we can write no claim as the negation of the claim, the duty as the correlative of the claim, the liberty as the negation of the claim negated action. And by doing so, what we can do is that we recognize 4 positions, and we recognize as well a subalternation relation, which is sufficient for us to construct the first square of opposition. So this will be the claim-based square of opposition. Then we pass to the second order of Hoeffeldian concepts, which are far less studied in the literature. We will start from a definition based on the concept of ability that me and Matteo, we worked out actually last year and we presented here at the CILC workshop. So we will do that by utilizing the concept of ability. So the ability is a kind of causal mechanism, a description of a causal mechanism. So there is an agent that by performing a certain action, which can be seen as a kind of stimulus, produce a certain effect, which is a manifestation of the word. So by performing the action type beta, the agent X is able to produce in the world a new institutional position according to which X has a claim towards Y of performing A. So that means that Y has a duty towards X of performing A. And we call that power. So this is the canonic form of power that's about the ability of creating a duty. So X is a power towards Y to create a duty concerning A if there is any type of stimulus that can produce that as an effect. Then we can use this primitive, this ternative primitive, to define all the others, just as we did for the claims. But then how we can construct an Aristotelian square out of this? Because actually this is really, there was a gap. We haven't found anything in the literature that was trying to do the same. And in this work, we individuate 3 distinct forms of power. So the first type of power was analyzed first by Sumner and then later by Oreilly a few years ago. And so the question is that the notion of power, it's about the ability of a certain party to affect another party with respect to a certain relation. Then we can redefine this idea by using ability and focusing on the canonic power. So R, it's about a beauty. So that means we have the power of Oreilly, of one person towards another person, by performing B of having of obtaining as an effect a duty towards A, means that the X has an ability both to either to produce the duty or to produce the prohibition or to create a partial liberty upon Y. So these are all the relations which are related to the duty, because by creating one of those, automatically you create a change concerning the central position there. So by starting with that, we can define a positive type of change-centered power and a negative one. So if there exists one action such that produces a change concerning A, then there is a positive change-centered power. If there is if there is an action that doesn't have this power, so that means there is an action that the agent can do without modifying that relations, then it has a negative change-centered power. By utilizing these definitions, we have again 4 positions, and we can recognize a subalternation relation. So we can construct a square of opposition. And actually, this was the point that we found in the literature by starting from the work of Oreilly. So notice that in this case, the positive change-centered power is in the I position. Then in previous works, we recognized that we made an analogy of the concept of power with the concept to physical notions as attraction and repulsion. So we can actually define a force-centered power in which the attraction corresponds to a positive force power. So the power to attract a kind of certain actions of type A. So that means I can create a duty to perform that action. While the negative force will be I have the power to repel a certain action. So I can define that by utilizing ability as X as the power by declaring A, that will be a kind of command, to create the duty upon Y. While the negative power, negative force power, will be that by saying A, then Y will have the opposite. So we'll have a prohibition of doing that. So we have the same stimulus, but we have opposite manifestations. Again, we were able by doing so to create 4 positions and then to recognize a subalternation relation. And by this, we constructed a square of position in which the positive force power is in the position in the higher position, so in the A position. We have then the third type of power, it's the outcome-centered power. So we say that the canonic power is about the power to issue a duty, but we can also have the power to release from a duty. So we can utilize ability again to define that. And by doing so, we recognize another set of 4 positions and another subalternation relation that allows us to construct a square of opposition. So at the end, we have 3 power-based square of oppositions. And an interesting question is how they are connected. So we constructed a map in which we see all the relationship that gives an idea of the different level of abstraction, which actually makes sense in the first one, we look also at the relationship. So this is the force-centered power. It's about the relationship between the stimulus and the outcome. The second one, it's the outcome-oriented power. So that's about creating a duty or releasing a duty. And the third one, it's about the power of producing any type of change with respect to the duty of performing a certain action. So it makes sense that this is an abstraction over the other one. And actually, if we make it richer, we can see that there is a richer connection still, because this corresponds actually to a richer disjunction, and we can find also a relation in the lower level of this hexagon. Matteo, can you join now, or do you want to continue from?
Maybe I can join now.
Yeah.
Okay, if you want to keep the screen shared. So another point that we addressed was the possibility of expanding these squares of opposition into hexagons of opposition, because we found that in the literature there were some issues about the symmetrical treatment of first order and second order relations. So for instance, here you see that the last relation on the left includes a reference to action complementation, whereas in the list of relations on the right, there is no reference at all to action complementation. So this is one of the aspects of the asymmetry that can be dealt with by moving from squares to hexagons of opposition. And in general, the problem with squares of opposition is that they only provide a partial characterization of liberties, because having a liberty with respect to an action A means that one has both the possibility of performing A and the possibility of not performing A, whereas Aristotelian squares only provide a characterization of negative liberty, so a half liberty. And via symmetry, we also get another concept of duty that is more general, the notion of an absolute duty. So there is an absolute duty with reference to an action type A, if and only if A is either prohibited or obligatory. So when A is the object of a command in general. And putting together all these ingredients, we found that it is possible to provide more refined geometrical representations of first order and second order relations by adding deductive relations between the various concepts that we have analyzed so far. And this is a novel representation that has never been considered in the literature. There are related approaches that are based on prisms, but this opens the way to a further analysis in terms of more complex diagrams for Hohfeldian first order and second order relations. And then the last thing that we addressed was the analysis of relations between first order and second order concepts. These have been studied by Andrews and other authors, but Andrews is the one that focused more on this problem, providing what he calls a Hohfeld's cube, that is a solid in which relations of the first order and of the second order are combined, and there are new kind of connections, like causal connections, that constitute a bridge between, for instance, the second order and the first one. However, the problem with this kind of representation is that it is very far from explaining which is the logical theory behind these connections. So it is still open as a problem to figure out how this cube could be transformed into standard Aristotelian solids of opposition. And I think that this concludes our talk. Thanks for your attention.
Thank you, Matteo, and thank you, Giovanni. So perhaps thank you also for ending up at 6 precisely. So we have room for one question, and then we can conclude the session. Is there any question from the audience or from Parma? So otherwise, I will make one. What's the next step? The image. Oh, there is one from Parma actually. Yeah, please.
No. I don't. No questions from me.
Okay. So, what's the immediate next step?
The next step is that. Oh, sorry.
No, this was for the speakers, I guess. So, from my point of view, if I may, an interesting thing is applying these graphical devices to the analysis of, for instance, legal contracts. Because when a person tries to navigate a contract, sometimes there are synonymous claims that are not immediately understood as such by the reader. And a diagram of opposition, in particular an Aristotelian polygon, can help the reader in figuring out which is her position with respect to other normative parties. Furthermore, since diagrams work on finite sets of formulas, in principle, they are able to yield a decidable theory for reasoning about, for instance, implications between various positions. This means that one does not need the full power of a first-order logical system. It is enough to have a proper subsystem of that for efficient reasoning.
Thank you, and good luck with this new line then. And I thank you again, all the speakers and the attendees, both online and in Parma. And the session is over. Thanks.
Thank you, Stefano. Thank you to all the audience.